Good morning, ma'am.
Yeah, so I hope people will be joining soon. So let's start with today's class. Okay, so did you try to solve the problem which I gave yesterday? Fine. So let's discuss about that problem and then we'll move on. We'll continue with today's topic. So, oh, my screen is visible, right?
Yes, ma'am.
Okay. So the problem that was given yesterday was that you have an open loop feedback. You know the transfer function of a unity feedback system, and the specifications which the system should satisfy were given that the peak time should be equals to 1 second and peak overshoot should be equals to 10%. Okay, so it was so you were supposed to find what will be the value of k, so that k, which is the gain of the system, so that both these conditions are satisfied. So in order to find that, first of all, so we already know what will be the expression for a, so this is a second order system. So the moment you have a second order system, we have already calculated, or we have found out what will be the expressions for this peak time and this peak overshoot. Okay, so if you write the expression for this peak overshoot, you see that MP is basically dependent only on the value of the damping ratio, which is zeta. So since the value of this peak overshoot is given, so from here you can find what will be the corresponding value of zeta. Okay, so once you know the value of zeta, so then the next step would be to find out what will be the value of omega n and correspondingly the value of k. Okay, so for that, what you need to do is that you have to write the characteristic equation for the system. So if this is GS and it is given that the feedback is a unity feedback, so that means HS is equal to 1. So that means you can write the characteristic equation will be equals to 1 plus GS HS, which is nothing but S into S plus 2 plus K, which is equals to 0. And if you compare this equation with the standard, the generic form of the characteristic equation of a second order system, which is given by this. So this is the general form. So now if you compare these two equations, so you see that the value of 2 zeta omega n will be equals to 2. So from here you already know the value of zeta, so you can find what will be the value of omega n. So you know what is omega n. And here by comparing these two terms, you see that omega n square is equals to k. So since you know the value of omega n, so you can find what will be the value of k. So you know that, so from here you can find out that for this value of k, that k equal to 2.78, for this value of k, this condition, that is the peak overshoot will be equals to 10%, this condition is satisfied. Now in the second step, what we need to do is that we have to see that whether for this value of k, we are getting the value of this peak time as 1 second. If we get if for k equals to 2.78, the value of TP is equals to 1 second, then we'll say that this is the value of k for which both the conditions are satisfied. If not, then we'll move on to the next step. Okay, so for finding the value of this peak time, you see that peak time is given by this expression pi by omega n square root of 1 minus zeta square. Now this omega n and zeta, both the values are known to us, so you can substitute those values and you will find that the value of TP is equals to 2.36 seconds. So this is not equal to the specified uh, peak time, right? So that means we can say that for this k, so there is no one value of k which will be able to meet both the conditions which are given. So using this value of k equals to 2.78, this condition, this MP equals to 110%, this condition will be satisfied, but the other condition will not be satisfied. So then the second part of the question comes that, so then what would be the value of k so that both this TP and NP, they are violated by the same percentage. Okay, so they are violated by the same percentage means, now let's assume that the value of TP is now is changing from 1 second to, by let's say it is changing by x some percentage which is given by x. So then you can write that TP will be equals to 1 multiplied by 1 plus x. Similarly, MP will also be given by 0.1 into 1 plus x, because it is given that both of these two parameters should be violated by the same amount. So that means 1 plus x will be multiplied in both the terms. So similarly, so once you have this, so again you can compare the equations with, so again you have omega n equals to square root of zeta, square root of k, and similarly from here you can find what will be the expression of this peak time, right, in terms of k. Now k is unknown to you, you want to find out what will be the value of k. So in terms of k, you get this expression pi by square root of k minus 1 will be equals to 1 multiplied by 1 plus x. Similarly, for this condition, when the value of MP is given, if you put the values of zeta in this expression, you will get a second equation. So now you have two equations with two unknowns. So one unknown is k, another unknown is x. So then if you solve these two equations, you will find that the value of k becomes equals to 4.25 and x is equals to 0.75. Now, so here you can say that when the value of k is equals to 4.25, at that again the value of the peak time is equals to approximately 1.74 or 1.75 second, and the value of MP has increased to 17.5%. So that means in both the cases the percentage change in this value remains the same. So if you have a gain of 4.25, then both the parameters which have been specified to you, they will be the change in the parameters will have the same percentage change. So then the second part is also done. So in the third part, it's given that suppose you have, so initially the given was GS was equals to K by S into S plus 2. So that means that the pole at, there is a pole at S equals to minus 2. So now if you have a pole, so this pole at S equals to minus 2, let's say this pole can be now, it's a variable pole. So you can change the position of the pole. So let's say the position of the pole will be equals to now S equals to minus alpha. So now you will have to find out what will be the value of K and alpha. So here also now you have two variables in your system. So what will be the value of K and alpha such that the initial two specifications which were given, that is TP, and so such that TP is equals to 1 second and MP is equals to 10%. Okay, so this is the criteria that you need to satisfy, and for that you have to find out the value of K and alpha. Okay, so similarly for this, initially to start off with, obviously you will have to write the characteristic equation, and from the characteristic equation you will express the value of omega n and alpha and zeta in terms of the unknown terms. Okay, so once you know the value of omega n and zeta, then you can just simply put those values in the expression for MP as well as the expression for TP. So the moment you put the expression over here, and then just by solving these equations, you will find what will be the value of omega n. So all the informations that you need to find the value of K and alpha, they are known to you. So K is dependent only on the value of omega n. So omega n you have already found out. So that means you can find K will be equals to 15.4. And for alpha, you know the value of zeta you already know, because in the first case, we have seen that for MP equals to 10%, the value of zeta is equals to 0.6. So 0.6, so zeta is known to you, omega n is known to you, so you can find what will be the corresponding value of alpha. Okay, so if the gain of the system is 15.4 and the pole is placed at S, and if you keep the pole at S equals to minus 4.7, under these two conditions, the given specifications will be satisfied. So you have to design your system in such a way so that you have to design your system. That means that you can change the overall gain of the system, you can change the position of the pole of the system in order to meet the specific criteria which has been provided to you. Okay, so clear? Do you have any doubts in this? since no one is responding, so I hope that you don't have any doubts. So there are a few more problems I have provided for you to practice at home, so that you will have an idea about how to, whenever you are given with a system and the corresponding time response specifications are provided, how can you design the system and how can you find out what will be the corresponding zeta or omega n of the system that you have been provided with. Okay, so you try to solve these problems at home. The answers are also given, so you can always cross-check your answer with this and see whether you have correctly solved the problems or not. So now next we'll move on to discussing about the stability of a system. Okay, so initially when we were talking about the stability of the system, so we saw that if you have a bounded input provided to your system, if for that corresponding bounded input you get a bounded output, then we say that the system will be stable. Okay, so that means that, so if you want to find stability from that bounded input output condition, so you need to know what will be the expression for your output of the system. But whether so in order to make life sort of easier, or from the design point of view, so we have different kinds of stability, different kinds of methods by applying which you can simply find out the stability of a system without finding out what will be the output of your system. Okay, so out of these different kinds of methods, so one is called the Routh-Hurwitz method. So this Routh-Hurwitz criteria, basically this is an algebraic method, and it provides information about the absolute stability of a linear time invariant system. So absolute stability means using Routh-Hurwitz criteria, you will be able to tell whether a system is stable or is it unstable. So actually using this Routh-Hurwitz criteria, it actually tests whether any root of the characteristic equation. So any root of the characteristic equation means that's the pole of the closed loop system, whether any pole lies on the right half of the S-plane. So if the so it tests whether all the poles, whether they lie on the left half of the S-plane or there are some poles which are lying on the right half of the S-plane. Also, the number of roots that lie on the imaginary axis and on the right half of the S-plane, they are also indicated by this Routh-Hurwitz criteria. Then we also have something which is known as Nyquist criteria. So this Nyquist criteria, this is basically a semi-graphical method and it provides information about the difference between the number of poles and zeros of the closed loop transfer function. If you observe the behavior of the Nyquist plot, and from there you can find out what will be the difference between the number of poles and zeros and the relative location of the zeros. So depending on the information that you have on the location of the zeros of the closed loop transfer function. Okay. Then similarly we have something known as root locus. So root locus plot, basically this is a diagram for where you have or rather you study the locus that a root root of the characteristic equation it follows whenever a certain system parameter is varied. Okay, so if we will talk about this root locus Nyquist criteria subsequently in our in the next classes. And then you have something which is known as Bode diagram, and you have Lyapunov's stability criteria. But this last Lyapunov stability criteria, this is generally used applicable for determining the stability of non-linear systems. So this is not within the scope of this course. So this maybe later on, if you have this non-linear control in your if you study non-linear control, then this Lyapunov's stability criteria will come into picture. Okay, so now first of all we'll discuss about Routh-Hurwitz stability criteria. Okay, so basically this Routh-Hurwitz criteria, it is a method of determining the position of the roots of a polynomial, provided that the polynomial has constant and real coefficients without actually solving for the roots. So what is the advantage of using Routh-Hurwitz criteria is, first of all, it is applicable for both single and multiple input, multiple output systems. It can be used if you have a single loop system or a multiple loop system. And the best part about this Routh-Hurwitz criteria is that, suppose if you are given with a system of a very high order, so obviously solving a very high order equation, that becomes little tedious. So if you want to find out what are the roots of the characteristic equation of a high order system, then the calculation or the computation becomes much more complex. So Routh-Hurwitz criteria basically will tell you that if we can observe the characteristic equations and without solving for the roots of that characteristic equation, how we can find out whether the system will be stable or not. Now, if you know the roots of a system, then if you know the roots of the characteristic equation, or that means the poles of the system, so you, from the position of the poles, you can say that, okay, if the poles, they are lying on the left half of your S-plane, the system will be stable. If they're lying on the right half of the S-plane, then the system will be unstable. Right. So here what we'll do is that just by analyzing the characteristic equation, we'll find out whether there are any roots of this characteristic equation lying on the right half of the S-plane. So if you see, so this is a general form of a transfer function. So this is expressed in a polynomial form. So you have a numerator polynomial, you have a denominator polynomial. So this is basically an nth order system, you can say. So the characteristic equation for this system will be equals to this denominator. So this denominator equals to 0, that is the characteristic equation, and provided that all the coefficients, this a0, a1, an minus 1, an, all these all these coefficients, they are real. Okay, so in this Routh-Hurwitz criteria, so there are two conditions which need to be satisfied for you to say whether a system will be stable or not. So there is one necessary condition and another sufficient condition. Okay, so obviously the necessary condition means if the control system, it doesn't satisfy the necessary condition, so you can straight away say that the system is unstable. Now let's say that if the control system satisfies the necessary condition, then you will say that the system may or may not be stable depending on whether it is satisfying the sufficient condition or not. So once the system is satisfying the necessary condition, you then need to move to calculation or finding out whether the system is satisfying the sufficient condition in order to say whether the system is stable or not. So what are the necessary conditions? So the necessary conditions for stability is that all the coefficients of the polynomial must be positive. Okay, so either all, or you can, in other words, you can say that all the coefficients should have the same sign. So in case you are given with a polynomial, if you have the characteristic polynomial with you, and if all the coefficients of that polynomial are positive or have the same sign, then you can say that okay, the system is satisfying the necessary condition, and then we will move to checking whether the sufficient condition is also satisfied or not. So that means that so what is the so before moving into the sufficient condition, so suppose you have been given with a polynomial which looks like this: a0 is to the power n plus a1 is to the power n minus 1 plus dot 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 till an minus 1 into s plus an. Okay, so now the necessary condition is that all these values of a0, a1 till an, all these values should be positive or they should all be of the same sign. If they are negative, then all these a1, a0, a1 till an should be negative. Okay, so if that condition is satisfied, then you will say that the system is stable. But in case you see that, let's say one of these coefficients, so let's say that a0 till an, everything is positive except this a1. So a1 is a real value with a negative sign. So then you can say that straight away, you can say that the system is not satisfying the necessary condition and it is an unstable system. So you don't need to go and analyze for the sufficient condition. Now, once your system has all positive coefficients, then you will go to the sufficient condition. The sufficient condition says that if you find out the Hurwitz determinants, we'll just see what Hurwitz determinants are. Then all the Hurwitz determinants should be positive. If you can satisfy this equation, this condition that the Hurwitz determinants, that is dk, they are all positive, then you will say that the polynomial is satisfying both the necessary as well as the sufficient condition, and correspondingly the system is stable. So this, by definition, this Hurwitz determinants, if you see this polynomial, so then D1 will be given by A1, then D2 will be a determinant which is formed in this equation, this form. So you have A1 and A0 in the first column, and then you have A3, the third term, the A3 and A2 in this way. Similarly, if you want to find out for the D3, so D3 will be A1, A0, and then the last element of this column will be equals to 0. Then in the second column you will have A3, A2 and A1. In the third column you will have A5, A4, A3. So you see, in the first row we actually have all the coefficients for the even terms. See, A1 is the coefficient for the second term. So this is the first term, this is second, and so on and so forth. So you have all the even terms, the coefficients of the even terms, they are there in the first column, first row, you can say. So similarly, if you can find out what will be the value of this determinant. So now, as you can see that if you have been given with a polynomial, like let's say of 6th order or 7th order, then if you have to find out all these determinants, then it obviously becomes a little bit, it requires a lot of calculation. So as an alternative for that, so what has been proposed is that the sufficient rule, it has been simplified by Routh. That's why this name comes, this Routh-Hurwitz stability criteria, in form of a tabulation. Okay, so we'll just see how this tabulation is done. So let us say that if you have this, this is the polynomial which is provided to you. So A0 is to the power n plus A1 is to the power n minus 1 till this point. Okay, so the first step in formulation of this Routh array for checking whether the system is stable or not is that you will have to make two rows. Okay, so what will the two rows have? The first row will have the coefficients or the coefficients of the odd terms. So the first term, third term, fifth term. So all those coefficients will come in the first row. And in the second row, you will have all the coefficients for the even terms. That is the second, fourth, sixth, eighth. All these will come in the second row. Okay, so once you have formed these two rows, then what you will do is that we'll subsequently form other rows, and then we'll check whether the condition goes like this. If all the elements of the first column of the Routh array, they have the same sign can be either positive or negative, then we say that the system is stable. But if you have any kind of sign change between the elements in the first column of the Routh array, then the number of sign changes that are there, that will give you the number of roots of the polynomial which are lying on the right half of the S-plane. Okay, so let us say that you have been given with a 6th order polynomial. Okay, so now so the 6th order polynomial will be like A0 is to the power 6 plus A1 is to the power 5 So this is the polynomial, 6th order polynomial which is provided to you. Okay, so let us see how to find out or how to make the Routh array first. Okay, so the first column will have all the odd terms. So that means the first column, the first row will have all the odd terms. So that means A0, then so you will have A0, A2, A4 and A6 in the first row. Okay. Similarly, in the second row, you will have all the even terms. So you will have A1, A3 and A5. You don't have a fourth even term, so we will have just 0 in the fourth element. So you have A0, A2, A4, A6 in the first row. In the second row, you will have A1, A3, A5 and the last term is not there, so it will be 0. So then and in the left hand side we will have one more column. So this column is just for our this has, so we will write all the powers of S. So starting from the highest power, so since this is a 6th order system, so S to the power 6 corresponding to the first row will denote the element in this column will be S to the power 6. So then the second one will be S to the power 5 and so on and so forth till we get to the last term, which is S to the power 0. Okay. So now what we'll do is that we'll fill up the whole table. So filling up the table, it goes like this. The first element of, so these two, the first two rows will come from the information which is provided in the from the polynomial, and from the third row onwards we have to do the calculation. So this calculation goes like this. So for the first term, so what you will do is that you will simply multiply these two terms, A1 multiplied by A2 minus A0 multiplied by, so you start from this term, multiply it with this, come back here, multiply A0 with A3 and take the difference of those two and divide it with the first term that you have. So this term will be equals to A1 A2 minus A0 A3 divided by A1. Similarly for the second term, so what you will do is that you will start from A1. Since we are dealing with this row, always it will start from the first element of the previous row. So for the second term, you will start from A1. So you will multiply A1 with A4 and then we will multiply A2 with A5, take the difference and divide it with A1. So you have A1 A4 minus A0 A5 divided by A1. For the third term, you will have A1 A6 minus A0 multiplied by 0 divided by A1, which is nothing but equals to A6. So that means the third row, the computation of the third row is done. Then you move on to the fourth row. Okay. In the fourth row also, you will find the elements in a similar way. So in the fourth row, what you will do is that, so this will become your first, so you will start from this row. So you will multiply this element A with A3, then take minus of A1 with B divided by this element A. Similarly for this term, you will multiply A with A5 minus A1 with A6, then divided by A. And for this term, you will have A multiplied by 0 minus A1 multiplied by 0. So this term will become equals to 0. So all these subsequent terms, so once you have 0, so that means these subsequent terms will be equals to 0 from the next step onwards. So in a similar way, you have to fill up the whole table. Okay, so once you have filled up the whole table, then what we need to verify is that then we will see what is the, we will observe the first column of this Routh array. Okay, so now if you see that if there are no sign changes between A0, A1, A, C, E, F and A6, if all these terms they have, so if A0, A1, A, C, E, F and A6. So if all these terms they have the same sign, be it positive, be it negative, if all of them are of same sign, then you will say that the system is stable. But if they have some different sign, so let's say this, so all of them are positive except for, let's say, A. So A is a negative term and then again E is also a negative value. So that means there will be, like, there is one sign change here So this is positive. So from positive to negative, you have one sign change. Again, C is also positive. So from A to C, you have another sign change. Again, from C to E, another sign change, and E to F, you have another sign change, right? So that means you have 1, 2, 3, 4. So you have 4 sign changes in the first column. So that means the number of sign changes will indicate how many poles or how many roots of this equation are lying on the right half of the S-plane. So the moment you see that there are poles lying on the right half of the S-plane, so you can say that the system will be unstable and there will be this many number of poles which are there on the right half of the S-plane. Okay, so then this we have already told that then we will, after you have tabulated or you have formulated the Routh array, then you have to find out, you have to investigate the signs of the numbers that are there in the first column. So if the roots of the polynomial, they are all in the left half of the S-plane, if all the elements in the first column of the Routh array have the same sign, but if there are changes in sign of the elements in the first column, so the number of sign changes will indicate how many roots are there with positive real part. So that means how many roots are lying, or you can say how many roots lie on the right half of the S-plane. Okay, so now if you want to see the, so this is the Routh-Hurwitz stability criteria. Okay, so if you want to see the relation between the first column of the Routh array with the Hurwitz determinant, so you see that the first column of, so you can write the first column as A0 is equals to 0 and A1 will be equals to D1. If you remember the value of this Hurwitz determinants. So the Hurwitz determinants showed that the value of D1 is equals to A1. So that means the first element of the first column is equals to D0. So D0 is equals to A0. Then the second element will be equals to D1. Similarly, if you see the, so D2 was given by A1, A0, A3 by A2. So this is nothing but A1, A2 minus A0, A3, right? So then the third one, similarly, you can find out what will be the value of D3 and so on and so forth. So if you calculate these values, you will see that the first column of the Routh array, that is actually related to the Hurwitz determinants in this way, like the third element will be equals to D2 by D1, the fourth element will be equals to D3 by D2. So here also you see that we had actually told earlier that all the Hurwitz determinant will be of positive, should be positive. So that means if there are no sign changes in the first column, so that means all these values, they have the same sign. So that means that this modification or the simplification which Routh did for calculation of this stability, that is actually satisfying the criteria which has been provided by Hurwitz, that is in terms of the Hurwitz determinants. Okay, so now let's try to solve a few examples, then maybe it will become a little bit more clearer to you. So you have, let's say you have been given with a characteristic equation which is given by something like this. So you have s to the power 4 plus 3s cube plus 3a square plus 2s plus 1 equals to 0. So the first thing that you will do is that you will check whether all the coefficients have of this characteristic polynomial, whether they are positive, real positive or not. So in this system, you see all the coefficients are positive and they are all of the same sign, right? So that means you can say that the system satisfies the necessary condition. Okay, so since the system satisfies the necessary condition, now what we'll do is that we'll form the Routh array and then we'll see whether the sufficient condition is also satisfied or not. So the first column or the first row will be equals to the first term, third term, and the fifth term. So you have 1, 3, and 1 over here. In the second column, you will have this second. In the second row, you will have the second term as well as the fourth term. So you have 3 and 2 over here. Now we will compute the other elements of this route array. So for this s to the power 2 row, you will have 3 multiplied by 3 minus 1 multiplied by 2 divided by 3, which is equals to 7 by 3. Then the second element will be 3 multiplied by 1 minus 1 multiplied by, here you don't have anything, so you have 0 basically over here. So you have 3 minus 0 by 3, which is equal to 1. So this row is also done. So you move on to the next row. So in the next row, you will have 7 by 3 multiplied by 2 minus 3 multiplied by 1 divided by 7 by 3. So that will give you 5 by 7. Then you in the next one, so you see that both these are all zeros. So multiplication of these will give you 0. So we will not compute anything else over here. Then for the last term, you will have 5 by 7 multiplied by 1 minus 7 by 3 multiplied by 0. There is nothing over here, so 0 divided by 5 by 7, which is equal to 1. So now if you observe the first column, so if you see the first column, all the elements in the first column, they are positive. So that means there are no sign change in the first column of the route array. So you can say that the control system is stable and all the roots of this system, they lie on the left half of the S-plane. Okay, so this is how the Routh-Hurwitz stability criteria goes. Okay, so now there are a few special cases in Routh-Hurwitz criteria. So the special cases being, there are some difficulties which may arise once you are forming the Routh-Hurwitz route array. Then one of the special cases is, let's say if the first element of any row in the route array becomes equals to 0. Okay, so here in this case we have seen that the first element is not of any of the rows is not equals to 0. Okay, the later elements can be 0, but the first element is not 0. So if you have if the first element somehow becomes equals to 0, so that means, and the other elements are not, in that case what will happen is that the moment you try to fill up the next row, so that means you have to divide it with 0, so that means the next elements in the row will become infinite. So obviously there will be a break in the route array. So what we'll do is that we'll have to find out a solution for that. So in such a condition, so what you will do is that first there are two ways of tackling this problem. So the first way is that you replace the element which is 0 with an arbitrarily small positive number epsilon. Okay, so once you put it with replace that 0 with epsilon, and then subsequently you proceed with the route test. You form the rest of the arrays, and once you have formed the array completely, then again you examine the signs of the first column and you examine the signs provided that the value of epsilon is tending to 0. Okay, so let's see, suppose here. So you have this equation s to the power 4 plus 2 s cube plus s square plus 2s plus 1. So you see, if you form the route array. Okay, so one more thing is that suppose if in a route array you have suppose here in the second row you have both the terms are equals to 1. So for simplification, what you can do is that if a row has a common factor, what you can do is that you can just simplify that row by dividing with the common factor. Okay, so here in the second row you have both the terms are 2, so we can just simply divide both the terms by 2 and you will get 1 and 1. So for simplification of the calculation, you can just divide this with any if the elements in the row they have a common factor, you can divide all the elements with that common factor and then correspondingly proceed with your formation of the route array. Okay, so in the first column you have 1, 1 and 1. In the first row you have 1, 1 and 1, and in the second row also you have 1 and 1. So if you calculate the first element of the third row, you will see that the first element of the third row becomes equal to 0. So if you want to calculate the first element of the fourth row, you will see that this fourth row, this element will become equals to infinite. So that means you can, so there will be an premature break in the Routh-Hurwitz array. So for that, as a solution, what we'll do is that we'll just substitute this value of value 0, this element 0 with, we'll substitute this with epsilon, and then we'll continue with the with forming the array. Okay, so if you substitute epsilon over here and then you form the array, so this, the next term will be equals to epsilon multiplied by 1 minus 1 multiplied by 1 divided by epsilon, which is equals to epsilon minus 1 by epsilon. So then your Routh array has been completed. Now you observe the value of these array when you have s is tending to 0, epsilon is tending to 0. So for epsilon tends to 0, you have 1 over here. You will have, since epsilon is tending to 0, so this will become a minus infinity value, and then the last value is equal to 1. So here you see that there are actually two sign changes. So from here to here you have, it's changing from positive to negative, and then again it is changing from negative to positive. So that means there are two sign changes which are there in the first column of the Routh table. So you can say that the system is unstable and there are two roots on the right half of the S-plane. Okay, so this is how you can tackle in one way the if you encounter a 0 as the first element of your Routh array, then you can tackle that using this kind of a solution. The other kind of solution, or the second solution that can be applied, is that if you substitute the value of s by 1 by z, okay, and then you substitute the value of 1 by z and write the modified Routh. So let's say you have an equation. So let's say this equation fs is provided to you. Then if you substitute s equals to 1 by z, then you write fz. You write the form of fz, and then simply you apply the Routh's test on the modified equation in terms of z. So in the modified equation means, again, just simply s, so you will have z to the, let's say if it's a 6th order system, then you will have z to the power 6, z to the power 5, z to the power 4, and so on and so forth. And similarly, you form the Routh table and then you do the Routh test. And if you have, if you observe if the number of roots with positive real part, if you have any sign change in the first column, so that means there will be some roots of z roots which will have positive real parts, that is they will lie on the right half of the z plane. So that will be equivalent to, you can say that since you have just substituted s equals to 1 by z, so you can say that if there are roots of this equation fz on the right half of the z plane, that is equivalent to the roots of this fs that will also lie on the right half of the s plane. Okay, so from there you can find out about the stability of the system. But the initial solution is, so the first solution is you will replace the element 0 with this the small number epsilon, and then continue with the Routh test. Okay, so this is one difficulty or a difficult solution which might come while solving the Routh array. Now the second case, there can be a case where all the elements on the Routh array are equals to 0. Okay, so in the previous case, only the first element of that row was equals to 0 and the other elements were not. But there might be cases where all the elements in a single row are becoming equal to 0. So what does that signify? If all the elements in a Routh array, elements in a single row of a Routh array becomes equals to 0, what does it signify? It actually says that this condition actually indicates that there are symmetrically located roots in the S-plane. Okay, so symmetrically located roots in the S-plane means that there can be a pair of, so the symmetrically located roots, they can be a pair of real roots with opposite sign. It can be a pair of imaginary roots with opposite sign, or it can be a pair of complex conjugate roots forming a symmetry about the origin in the S-plane. So in either, if any of these three conditions are present, then you will get the elements, then you will find that one row of this route array that has all 0 elements. So the moment you have an all zero row, so you can say that simply you can make a conclusion that the system will have either a pair of real roots with opposite sign, or a pair of imaginary roots with opposite sign, or a pair of complex conjugate roots. Okay, so how to deal with that kind of a situation? So then what we'll do is that, so you will form the route array and you will stop at the point where you have all zero row. Okay, so in the next step what we will do is that we'll write the equation which is formed by using the coefficients of the row which is just above the row of the zeros, and that equation is known as an auxiliary equation. Once you have written the auxiliary equation, you will differentiate the auxiliary equation with respect to S, and then whatever is the whatever will be the coefficient of the polynomial of this differentiated equation, you fill the rows of 0 with that corresponding with these coefficients, and then again proceed with the route test. Now all the roots of equal magnitude, since we have already said that there will be a pair of roots, either real roots or imaginary or complex conjugate. So all the roots of equal magnitude, they can be obtained if you solve this auxiliary equation. And also these roots of this auxiliary equation, they are also the roots of the original characteristic equation. So the stability of the system basically depends on the roots of this auxiliary equation. So let's see that if you have a system or a polynomial like this, if you find out, so you see that if you find the construct the route array, you will see that in the third row you are having both the elements are 0. So for what we'll do is that we'll go to the previous, so we'll take the previous row. So here also you see that all the rows, all the elements in the second row, they are 3. So that means we can simply divide them with the common factor and make it in a simplified form. So we can write 1, 1 and 1 over here. So, and in the third row you have all 0 elements. Okay, so the moment you have all 0 elements, then we'll go to the previous row and we'll write the auxiliary equation, and the auxiliary equation will be written in such a way that this first element will be multiplied with the coefficient of the first element will be multiplied with s to the power 4 plus coefficient of the second element multiplied by s square. So the so we will eliminate one order in between, and then we'll move to the second order of s, and then the last term will be equals to 1. So here, since the first term is s to the power 4, the second term will be s to the power 2, and the third term will be equals to s to the power 0. If you were dealing with this s to the power 3, let's say if s square, the row corresponding to s square were all zeros, then you will write the auxiliary equation corresponding to this s cube row. So then the auxiliary equation will be equals to whatever is the coefficient over here, that one multiplied by s cube plus this coefficient multiplied by s to the power 1 plus, if you obviously you will not have any element over here, so that will be equals to, so that this is the auxiliary equation. So the moment you have the auxiliary equation, now you take the derivative, and so the derivative goes like 4s cube plus 2s. Now what you will do is that you will substitute these two coefficient values 4 and 2 in the 0 element. So you will substitute 0 by 4 over here, and you will substitute this 0 by 2 over here. And once you have substituted that, then you will continue with the forming the rest of the route array. Okay, so now you have 4 over here, 2 over here. You can again simplify. You can, so this will become 2, this will become 1, and then you complete the route array. Once you have completed the route array, now you see that there are 2 sign changes. So from 0.5, you have a sign change over here. It goes to -3, and from -3, it is going to +1. So there are 2 sign changes in the first column of the route table. So you can say that the system is unstable. Similarly, so So similarly, if you have, so depending on what is the, how many sign changes are present in the system, accordingly you can find out what will be the value of the, what will be the number of poles or the number of roots which are lying on the right half of the S-plane. Okay, so the Routh-Hurwitz criteria, you can say that it is valid only if the characteristic equation is algebraic in nature and all the coefficients are real. Okay, so if any of the coefficients of the characteristic equation, it is a complex number or it consists of an exponential function, then Routh-Hurwitz criteria cannot be applied. Okay, and also using this Routh-Hurwitz criteria, it actually provides you only information about the absolute stability of the system. So it will only tell you whether the system is stable or it's unstable. So obviously, once you have found out that your system is stable by using Routh's test, so obviously we would want to know that how much stability, how good is, the system is, how much stable the system is, or how close the roots of the characteristic equation they are lying to the imaginary axis of the S-plane. So these kind of information, that is the information about the relative stability of the system, that is not provided by Routh-Hurwitz criteria. Okay, we can find the stability using relative stability using Routh-Hurwitz criteria to some extent, but that actually involves a lot of calculation or a lots of trial and error. So that is not a very viable solution for finding the relative stability using Routh-Hurwitz criteria. So mostly, and also if your system is found to be unstable using this Routh-Hurwitz criteria, it does not specify that how you can make or what changes in the system you should incorporate so that your system will get stabilized. Okay, so these are some of the advantages and disadvantages of the Routh-Hurwitz criteria, you can say. So we'll I think we have already reached at the end of the class. So what we'll do is that in next class, we will discuss more about this relative stability and I'll give you some problems which are, I think the problems are already here. So I will share you with some problems and you can try to find the stability of those kind of systems using this Routh-Hurwitz criteria. Okay, so is there any doubt in understanding this concept? Is there any doubt?
No.
Okay, fine. So then that's all for today. And also there is one more thing that I want to tell is that next week we will have the quiz on the second module. So we'll have the quiz after 28th because till 28th we are not supposed to, because of this science festival week, we are not supposed to take quizzes. So we'll announce the date for the quiz later on, but it will be held sometime in the next week. Okay, that is one thing. And the other thing is that I was just going through the attendance of all of you, and I found out that there are many students who have shortage of attendance till now. Okay, so I'll share the names of those students, and then just if you are there, if you are one of them, then please make sure that you are attending the next classes regularly. Otherwise, you will not meet the criteria for regarding the attendance for the final end-sem exam. So just take care of that. Okay, so that's all for today. So thank you, everyone.